welcome to section 1.6. This is going to be a quick review of exponential and logarithmic functions. So we'll take a look at the idea of exponential functions and the properties of exponential functions. We'll take a look at that magical number e, and we'll take a look at the natural log function and some properties of logarithmic functions. Okay, so exponential functions, we took a big long look at these. Should have done a whole chapter on them back in your college algebra. Basically what they are is they are a constant raised to a power where that power is the variable. Right? Like y or f of x equals 2 to the x. Right? 2 to the x, the base is the constant, 2. The variable is the exponent. And we can raise it to powers, and when those powers are rational powers, it's pretty straightforward. We know what it means. 2 to the 0, 1, 2 to the 2, that means square it, that means cube it, that means raise it to the negative 1 means, well, we'll take the reciprocal of it. Even some weird exponents, like a half, we know what that means. It stands for a root. It's a rational exponent, means that there's some sort of root involved. Okay? Now, real number exponents are kind of weird because there are some, like, that just don't make mathematical sense, like 2 to the pi. What does that mean? Well, the way that those are evaluated is that it's evaluated using a process of closeness, if you will, where they evaluate it for numbers that are close to pi, that are rational numbers, and then we can estimate it out to a certain degree of accuracy. You know, however far out you want to go, you just find a rational number close to it and evaluate it for that. There are some basic properties of exponents that we run across all the time in math, but in calculus too. Right? One of those properties being, what does a zero exponent mean? Well, the zero exponent just means that the base a raised to the zero exponent is always equal to 1, no matter what the base is, as long as it is a positive real number. A to the 0 is 1. Right? If you have the same base and you're multiplying two terms together, you add the exponents. If you have a raised or stacked exponents like that, you multiply the exponents together. Division down here, I'm going to skip number 4, come back to it, but division down here, number 5, you have a to the x divided by a to the y, same base, you subtract numerator minus the denominator to get your new exponent. Okay, and then I'll skip number 6, hop over here to number 7. A negative exponent just means take the reciprocal. Now the reason I skip these two is because both of those properties contain two bases. There's the base a and the base b. Now remember, a and b are both just numbers. Okay? And so number 4 says it's a times b raised to the x would be equal to a to the x times b to the x. So we're just taking two bases, like say if we had 3 times 4 squared, well that would just mean 3 squared times 4 squared. Now you might be looking at this and wondering, why would I do that? Why wouldn't I just do 3 times 4 is 12 and square 12? Well, that's probably what you would do. But the thing that you want to remember is, since every single one of these properties is written with an equals sign, they work from left to right and they also work from right to left. Meaning if you had something that was on the right-hand side and you wanted to simplify it down to the left-hand side, for whatever purpose, you could. All right, so let's run through some of these examples right here and evaluate them out. All right, so without using a calculator, we should be able to evaluate these. So for example, what does negative 3 wrapped up in parentheses raised to the 4th mean? Okay. Now mathematically, I know what that means. That means this, right? Multiply the base, negative 3, times itself 4 times. And I believe that's going to be 81. Okay, now how is that different? How is this different from this? Okay, well, what does the second one mean? And really what it relies on is it relies on a good understanding of the order of operations. The order of operations would say that this means, truly means, negative 1 times 3 times 3 times 3 times 3. Okay, this piece right here is the 3 to the 4th, and this piece right here is that negative sitting out in front. Now remember, when we put a negative out in front of something, it's a lazy shorthand for negative 1 times that value. Like if you say negative x, what you really should say is negative 1x, negative 1 times x. But we got lazy in mathematics and we stopped writing that 1 and we just accepted that everyone understands this. The problem is everyone doesn't understand this, and you'll be amazed at how many times. Oh, by the way, just to finish this problem out, 3 to the 4th is 81. This is negative 81, right? You will be amazed how many times these two problems are mixed up. And this is what's been written, and this is the answer that's given. Or this is what needs to be evaluated, and that is the answer that's given. Most commonly, this wrong negative answer shows up when you have something like this, x to the 4th, and we're told that x is negative 3, and we need to evaluate that. Okay? So just be careful of that. That's a common mistake. Watch what's happening. All right, what does it mean when we task you to do 3 to the negative 4th? Well, there's actually two things going on here. There's a negative in the exponent, and there's a 4 in the exponent. And each of those two things really do something different. Okay? What that really means to do is it really means to do 1 over 3 to the 4th, which you've established already is 81, so that will be 1 over 81. Right? Now, one of the things that you probably don't think about, but that is there, is there's a negative, but there's no negative in the answer. There's no negative even in the process of evaluating that answer. That negative there does not mean what a negative traditionally means. Right? It's the same symbol used in a different way. It's kind of like when we talked about inverses, how the negative 1 there is used in a different way. Okay? How about this? Okay? Now, I don't want to evaluate this because that's a big number, and that's a big number, and I'm supposed to do these without a calculator. So the last thing I want to do is try to figure out what 5 to the 23rd is. So once again, I'm just going to make use of a uncomplicated, a simple property of exponents that says when you have the same base, in this case, my base is 5. I really wish I was better at that. My base here is 5, my base there is 5, and if they have the same base, then I can just do a simple calculation. This becomes 5 to the 23 minus 21. 23 minus 21 is 2, so 5 to the second, and 5 to the second is 25. How about this one? Now there's a lot to unpack here because there's a lot going on. First off, my base is now a rational number. My exponent is a negative number. So I've got to do a whole bunch of stuff here. Now, if I were to write all the steps out, what I'm looking at here is I'm looking at 1 over the quantity 2/3 squared, which then becomes 1 over 2 squared over 3 squared, which is going to give me 1 over 4 over 9, which would then give me in the end 9/4. Now, I don't necessarily expect that you would write every single one of those steps out. You might skip 1 or 2 of them here. I definitely would have skipped this one. Okay? But what I would expect is that you could comfortably get from there to there. Right? So evaluating exponential functions. So what does this one mean? Because now the rational number is now the exponent. And so what I have to remember is that these two positions mean different things. The exponent in the numerator there means to raise, and in the denominator that means to root. Now the negative, that means reciprocal. So I got 3 things I have to do. I have to take the reciprocal, I have to raise it, and I have to root it. So do you want to do this? Or do you want to do this? Neither is more correct than the other. They will both get you the correct answer, but I will argue that this is not always a good way to go about things because I don't want to cube 16, especially if I have to do these things without a calculator. I would much rather prefer to take the 4th root. And the 4th root of 16, I'm sure you know, is 2. So this becomes 1 over 2 cubed. And 2 cubed is 8, so I get 1/8. And so my final answer is 1/8. So I'm just doing some uncomplicated, some simple calculations using exponents. Here are some more. All right, what's going on here? Well, I've got two terms being multiplied together, and one of those terms has an exponent attached to it. Two terms being multiplied together, and one of those terms has an exponent being attached to it. Right? Now, Aunt Sally taught me that I need to deal with exponents before I deal with multiplication, so I'm just going to leave that first term alone. But I'm going to deal with that second term. Now, the rules of exponents say that when you have an exponent attached to a single monomial term like that you need to attach the exponent or apply the exponent to each of the multipliers. So that's going to become 4 squared times a squared times b squared squared inside of those parentheses there. Again, leaving that first set of parentheses alone. I haven't done anything with this yet. 16 a squared b to the 4th. Where'd that 4 come from? Stacked exponents multiply. 2 times 2 is 4. Now that I've dealt with the exponent, I can do my multiplication. There's a constant here and a constant here, and I can multiply those together. 3 times 16. 3 times 10 is 30. 3 times 6 is 18. So 3 times 6 is 30 plus 18 or 48. I have an a cubed here and a squared there. That's going to give me a to the 5th. Remember, same base, add the exponents. A b here. Excuse me. A b cubed here and a b to the 4th there. Add the exponents. I have a b to the 7th. And I'm done. Okay, that's not too bad. How about this guy? 254 raised to the 0 power. Well, any number, not 0, raised to the 0 power is always equal to 1. Why is that? Well, what it is it's a consequence of this rule, right? That rule that said that a to the m divided by a to the n is equal to a to the m minus n, or what letters does Larson use? Larson uses x's and y's, m's, n's, doesn't really matter, right? What if these two were the same? What if it was a cubed over a cubed? Well, I learned a long time ago that when upstairs and downstairs are the same, that's equal to 1. But if I attempt to apply this rule to it, I get this. Well, somehow, mathematically, these two things have to be the same. Because you can't have something be equal to 1 and have it be equal to something else at the same time. It's either equal to 1 or it isn't. And so for it to be equal to 1, that must mean or imply then that a to the 0 is equal to 1. Okay, our last one. I need to clean this mess up. Now, it looks like I got a lot going on here. I've got a numerator with x terms, x's in the denominator, y terms and y terms in the denominator. I got a negative exponent down here. I got a negative exponent out there. I'm not sure what to do. So what I am going to do is I'm going to start inside of the parentheses. And I'm just going to deal with things. Okay? Oops, I don't want that. I got a 3 times x to the 3 halves times y cubed over 1 times x squared times y to the negative 1/2, and this is all raised to the negative 2. Now you may be wondering why I just did what I did. Well, I wanted to rewrite this so I could see everything that's going to play together. The 3 and the 1 play together, the x's play together, the y's play together. And now what I can do is I can simplify each multiplier, and then once I'm done simplifying inside of that set of parentheses, I can deal with that negative 2. Now, luckily for me, there's not much to do with 3 and 1. 3 and 1 is just 3. But what's going to happen here? Right? Well, the rule says to take the numerator exponent and subtract from that the denominator exponent. So what is 3 halves minus 2? Well, 3 halves minus 2 is negative 1/2. Negative 1/2 means it ends up downstairs as a positive 1/2, right? Okay. Now what's going to happen here? Well, using the same rule, I have the same base downstairs and upstairs. The base is the y. I have an exponent upstairs and an exponent downstairs, so the rule is to take the numerator exponent and subtract off the denominator exponent. So 3 minus a negative 1/2 really means add 1/2, so that's what 7/2. And so I get y to the 7/2. And this is all still raised to the negative 2. So what does negative 2 mean to do? Well, since this is a multiplier situation here, there's multiple things being multiplied together, I need to apply that squared to everything. And then what does that negative mean to do again? Oh yeah, flip it all upside down. So then I'm going to flip it upside down. It's going to become x to the 1/2 squared over 3 squared times y to the 7/2 squared. And actually those big parentheses are on the outside I no longer need, so I could get rid of these. And now one last step to clean it up. X to the 1/2 squared is just plain old x. 3 squared is 9, and y to the 7/2 squared is y to the 7th. And so my final answer is x over 9y to the 7th. Exponents. Well, what if we take and turn an exponent or an exponential term into an exponential function? Well, exponential functions, in the big picture, have two shapes. Exponential growth, left to right it goes up, or exponential decay, left to right it goes down. So we look at how something gets bigger or how something gets smaller. What drives this? Well, if that a is a number greater than 1, it's all about the exponent. If the exponent is positive, then it's a growth situation. If the exponent is negative, it's decay. There are some basic properties of exponential functions. Fairly certain you've seen these before. Domain is all real numbers. Range is just 0 to infinity. They have an intercept at 0, 1, and these are one-to-one functions. Now this should jump out at you because if it's a one-to-one function, that means from last section, this thing is going to have an inverse. And what do you call the inverse of an exponential function? A logarithmic function. So the inverse of the exponentials are logarithmic, and the inverse of the logarithmic are exponentials. Now there are lots of exponential bases, and so that means there would be lots of logarithmic bases. But in calculus, we primarily focus on one logarithmic function that has good properties, I guess I'll say, and we use it because it has those good properties, and that's the natural logarithmic function. And the reason we like the natural logarithmic function is because it's based off of that natural number e. Now, as we get deeper and deeper into calculus, you'll start to see why we really like that natural log function so much. Right now, you might be looking at going, I don't understand why it's so good. It gets better, okay? So the natural logarithmic function is defined to be the inverse of the exponential with the base of e. And so it reads, the natural log of x is equal to b if and only if e to the b is equal to x. And that's just the statement or the definition of logarithms. Right? Logarithmic function has a domain that is the range of the exponential, has a range which is the domain of the exponential. You notice that the intercept is switched, but it is still one-to-one. Do you remember the section when we talked about inverse functions? And we said inverse functions are beautiful reflections across that line y equals x. This is your exponential function, so this would be y equals e to the x. And then this gold one down here is your logarithmic, so this would be y equals the natural log of x. Okay? The horizontal asymptote that was here is reflected down to a vertical asymptote. That lovely intercept that was right there at the point 0, 1 is reflected over here to this lovely intercept of 1, 0. Okay? Logarithms and exponentials. Okay? There are properties of logarithms. There are 3 big properties of logarithms that you should know. That is that you can take a logarithm and rip the argument apart and turn it into the sum of 2 logarithms. you can take a logarithm of its division and rip it apart and write it as subtraction, and exponents can be pulled out in front. Now, we will be using these properties at different points all throughout the semester. And I'm just going to go back to what I said in one of the earliest videos I made, that one of the challenges with calculus is that anything can show up at any point in time. So exponential properties and logarithmic properties are just going to show up, and we're just going to use them. And the expectation is you look at that and go, oh, that's just an exponential property. I know that one. Or, oh, that's just a property of logarithms. I know that one. And we'll move on from there. All right. You know what feels really good about this? This is the last section in Chapter 1 review. The next video will begin Chapter 2. We don't have to start that until week 3, the start of week 3. We actually start doing calculus when we get to week 3. It is going to be fun. So if it's been fast up till here, it was supposed to be. It was review. It'll slow down and things will be better for you. The pace will be better. All right. See you for Chapter 2.